In this video, we are going to practice graphing cotangent, secant, and cosecant. And we will have changes in period, phase shift, reflections. Who knows? Stay tuned. Well, let's get started. Remember that the cosecant function is the reciprocal of the sine function. So, whenever I see cosecant, the first thing I'm going to do is graph the sine function very lightly, and that will guide me to my graph of the cosecant function. Now, please understand when you look at this equation that x over 2 is the same thing as 1/2 x minus pi over 4. Okay, so x over 2, it's like there's a little 1 there. X over 2 is the same thing as 1/2 x. Now, that means that we have a b value and a phase shift coming, but pi over 4 is not the phase shift. We are going to have to pull this 1/2 outside of the parentheses. You know what, let me zoom in a little bit closer. That's better on the eyesight. So I'm pulling out this 1/2. So if I do, I'm going to have 1/2. And then I'm going to have x minus. So to find out what goes here, I have to do pi over 4 divided by 1/2. So off to the side here, pi over 4 divided by 1/2. You have to multiply by the reciprocal. So this is pi over 4 times 2. So that's 2 pi over 4. So that's pi over 2. So this is going to be pi over 2, and that's going to be the phase shift. Alright, fine. So I have parentheses inside of parentheses. Alright, cosecant. So this is the version of the function that I should be looking at. Please stand by while I erase stuff. Okay, there is no a value, or I should say that the a value is 1. The b value is 1/2. That's going to change the period. And the h value is pi over 2, and that's going to be the phase shift. There is no k value. So first of all, the period. The period is always the normal period divided by the b value. For cosecant, it has the same regular period as the sine function, which is 2 pi. So the period should be 2 pi divided by this b value, which is 1/2. When you divide by a fraction, you multiply by the reciprocal, so that's going to be 4 pi. So the period is going to be 4 pi. X-intercepts and vertical asymptote equations, I'll do that at the end once I have the graph. Now the phase shift is this h value. It's the opposite of what it looks like. So when you have minus, it's actually a phase shift of plus pi over 2 to the right. Okay, so like I said, whenever I go to graph cosecant, first I lightly graph the sine function as a guide. So that's what I'm about to do over here. Now normally I would start the sine function right at 0 because of the way we know that the sine function normally starts right at 0. But there's phase shift. That's pi over 2 to the right. So for that reason, I'm going to start my graph at the phase shift. Alright, so I'm going to call this pi over 2. Alright, I could have picked this line or this line. I'm leaving myself room because the y-axis is going to be somewhere, and I'm not 100% sure where it's going to be yet. But I'm starting at pi over 2. And I know that the sine function is going to start there. Okay, because that's where it was phase shifted to. The period of the sine function is 2 pi, but let me start over. Every one of these marks represents 1/4 of the period. So if I count over 1, 2, 3, 4, this should be the end of the sine function. And remember how the sine function begins and ends on the midline. So the sine function will begin and end here. Now, I need to know the values of these marks in between. I need to label these. Now, when there's a phase shift, here's what I like to do. I know that each one of these marks represents 1/4 of the period, so I like to calculate what is a quarter period. Well, let's see. The period is 4 pi, so a quarter period will be 1/4 of 4 pi. In other words, 4 pi divided by 4, which is just pi. So pi is a quarter period. So I should be able to get these other values by adding this over and over again, alright, because that's a quarter period, and these marks are a quarter of a period. So I should be able to just add pi. Now, in order to add these, I need like denominators, though. So it would be helpful to make this into like denominators by multiplying by 2. Okay, so pi is the same thing as 2 pi over 2. So I can add that and it'll be the same thing. So that's what I'm going to do. Okay, so right here in the middle I basically have 1 pi over 2. Now I'm going to add 2 pi over 2 because that's the same thing as adding pi. So if I add 2 to 1, I get 3. So that'll be 3 pi over 2. If I add 2 more, that'll be 5 pi over 2. If I add 2 more, that'll be 7 pi over 2. And if I add 2 more, that'll be 9 pi over 2. Now I wrote these down here in case I needed to reduce something, but it turns out none of these reduce, so now I feel silly. So I'm just going to move them up. So I've got 3 pi over 2, and 5 pi over 2, and 7 pi over 2, and 9 pi over 2. Okay, I need to see where my y-axis goes so I can draw this thing. I think I'm going to go ahead and erase this work. So I'm done with it. And I'll erase this extra stuff. Okay, now I need to go to the left and I'm hunting for my y-axis. So if I were to subtract, remember that pi was, I shouldn't have erased it yet. Remember that pi was 2 pi over 2, and that's why I was adding 2 every time. Going to the left, I need to subtract 2 pi. So if I take 1 minus 2, that's negative 1. So this will be negative 1 pi over 2. And I already see that the y-axis is going to be right here. But just for fun, I just have one more mark here. If I subtracted 2 again, that would be negative 3 pi over 2. But the y-axis is going to be right here between the negative and the positive. Okay, so I'm going to go ahead and just draw my y-axis right in here. Okay. Now, the a value. The a value is 1. So I'm going to go ahead and just mark positive 1 and negative 1 about here and here. And I'm going to go ahead and draw the sine function. Okay. Now the sine function starts here, and then it goes up to its high value, and then it goes down to the midline, and then it goes down to its low value, and then back to the midline. So you know that the sine function would look like this. Don't draw it in, okay? You really could just leave the 5 dots. But if anything, just put a very lightly dotted sine function. So there's my sine function. But what I'm trying to graph, though, is the cosecant function. Now, because cosecant is 1 over sine, if sine is 0, then it's undefined. And that's going to give you an asymptote. So where is the sine function 0? Well, sine is 0 at these x-intercepts. So I'm going to draw vertical asymptotes right there, and I'm going to draw them as dotted lines. So we should have vertical asymptotes right here, okay, because sine is 0. And then I should have another vertical asymptote right here because sine is 0 here too. And sine is 0 here, so another vertical asymptote. Okay, now the cosecant function is going to be the same as the sine function here because the reciprocal of 1 is 1. And same thing down here. This is also the cosecant because the reciprocal of -1 is still -1. But from here, the cosecant function must, of course, approach these asymptotes. So it's going to go like this. Alright, you can see it's sort of, in a way, it's a reflection of this downward arch, and it's reflecting upward, but approaching the asymptotes. And similarly down here, this is going to be reflected down and approach the asymptotes. So the blue is the cosecant function. The dotted little sine function is just a guide. Alright, so that's it for the graph. X-intercepts, there were none. Alright, as you can see, it doesn't touch the x-axis. The cosecant function is shown here in blue. Vertical asymptote equations. See these green vertical asymptotes? They are going to repeat. See how they repeat twice every period. See this one in the middle? That's how you know it's happening twice every period. So basically every half period you're going to have an asymptote. So just start with the first one. I usually just pick the first positive one, so pi over 2. So vertical asymptotes always have the equation x equals, so x equals pi over 2. But now I'm going to add multiples of half a period. Half of a period would be 2 pi. So I'm going to add 2 pi, and I'll stick an n on it for the multiples. Alright, so I can get all of the asymptotes. Alright, I'll just let n be any integer. Alright, that way I'll get the positive asymptotes and the negative asymptotes when n is negative. And that's it. That's it for problem number 1. Okay, let's keep going. Let's roll right on. Okay, note that this is not cosecant of x plus 5 in parentheses. Alright, that means that this is a k value. This is a vertical shift. And that looks like the only special thing that's happening here. There's no phase shift. There's no change in period. So remember, cosecant is the reciprocal of the sine function. Well, I guess I should use x since they're using x. So this is just like the last problem. So the period, again, is going to be, well, the period is 2 pi because there's no b value. On the last problem, it became 4 pi because we had a b value of 1/2. But in the absence of a b value, or I could say when the b value is 1, it's just the normal period of 2 pi. We'll worry about the x-intercepts and the asymptotes later. There's no phase shift. If it were written like this with parentheses, then I'd have a phase shift. But there is no phase shift, so I'm just going to write none. However, this k value tells me that this is up 5, right? This is a vertical shift of up 5. Alright, so what am I going to do? Well, there's no phase shift, so I'm just going to start at 0 because I know the sine function starts at 0. And the way I graph cosecant is I start by graphing sine very lightly. So I'm going to just go ahead and draw my y-axis here and let that be 0. I actually for a moment I'm just going to write 0 down right here. So if this is 0, then if I go out 1, 2, 3, 4, then this should be my full period of 2 pi. Alright, there's no phase shift, so I can just do it using my common sense. Like half of 2 pi is pi, half of that is pi over 2, and this should be 3 pi over 2. Okay, so that's happening. And so here's my y-axis kind of doing its thing. And now, so let me be careful. So I need to do this shift of up 5. So I probably should leave myself some extra space up here. Okay, so here I go, counting my way up 5. So I'm trying to leave space. So 1, 2, 3, 4, 5. And I'm going to go ahead up one more to 6 because of the amplitude. So this is 5 right here. Okay, now this is going to be my new midline. So I'm just going to go ahead and put a dotted line right here representing my brand new midline. Okay, now you might not be able to see this very well on the video because I intentionally don't really want it to be that visible, but my amplitude is 1. Alright, we're talking about the sine function right now, and but the amplitude would be 1 because there's no a value. So from the midline I'm looking up 1 and I'm looking down 1. And I'm just giving myself a little bit of a yellow guideline. I don't know if this is even showing up on your screen or not, but that will help me when I draw my sketch in a moment. Okay, but I'm making it yellow because I want it to be faint. I want it to be really clear that this gray dotted line is the midline. Anyway, so we're talking about graphing the sine function first. Now the sine function is going to start at the midline. Okay, you know what, I should label these other, right, because this is 4 and this is 6. Alright, those are important. I should label those. So back to graphing the sine function. So it's going to start at the midline, and then I'm looking right here. It's going to go to its highest value, and then back to the midline, and then lowest value, and then back to the midline. Okay, so the sine function, alright, and again I'm just graphing this very lightly. Alright, there's my sine function. But the real graph I'm shooting for is cosecant. Alright, so the cosecant function is going to have asymptotes everywhere the sine function is at the midline. Okay, so these same 3 positions like before. Okay, so I'm going to go ahead and sketch in some vertical asymptotes. So there should be a vertical asymptote right here at the y-axis. But there should be another one right here at the midline. Alright, and there should be another one right here where the sine function touches the midline. Alright, those are my vertical asymptotes. Okay, now I'm ready to draw the cosecant function. Alright, the cosecant is going to be right here at the top of the sine curve, and it's going to stretch out towards those asymptotes. And it's going to be right here at the low point of the sine function. It's going to stretch out towards those asymptotes. Alright, so there you go. that is what the this cosecant function is going to look like. X-intercepts. There are going to be some x-intercepts here, right? Because eventually this is going to come down and hit. But honestly, I'm not exactly sure what I'm supposed to do for this. I'm going to have to get back to you on that. But the vertical asymptote equations. Alright, remember the vertical asymptote happens at every half of a period. See how it occurs right here in the middle of the period? It occurs at every half period. So I'm going to, my first one is right here at 0. So I could say x equals 0. And then I could start adding multiples of a half period because it comes in the middle. The period is 2 pi. So a half period would be pi. So I could say plus n pi. Alright? Multiples of a half period, where n is an integer. Okay, but 0 though. We don't need the 0. 0 plus anything is that thing. Like 0 plus 7 is 7. You don't need the 0. So I could just erase that, and I could just put x equals n pi. Alright, that gives me all of the asymptotes. Alright, this video is long enough, so I'm going to go ahead and stop it here. I will see you on the next video. Yeah, I will have to figure out about the x-intercepts and put that in the next video. Actually, let me just go ahead and say one more thing about these x-intercepts. There are x-intercepts, alright? Looking at these blue, they're going down, and eventually they will reach and cross the x-axis. So the x-intercepts exist. However, I think that this is beyond the scope of what we're trying to teach you right now. So I'm pretty sure that we really just don't mean to be asking you for the x-intercepts on this particular problem. Alright, that just slipped in there because all the other problems are asking for x-intercepts, and it's usually a reasonable thing to ask for. But on this one, it's just much tougher to find the x-intercepts than we mean to be giving you right now. So for now, just forget about the x-intercepts for this problem. I don't think we meant to ask you for them, if that makes sense.